Hello. So this video is going to be the final of 4 videos looking at working out how far away stars are. We've looked at parallax and we've come to understand parsecs and light years, and when speaking about parallax I did mention at one point that it only really works for the nearer stars. It doesn't work when stars are really far away, because it only works if we can see an observable shift, we can see an observable movement. If we can measure a parallax angle, that's great, and then we can do some sort of measurement, and we can be really good at measuring parallax angles. We can measure parallax angles that are thousandths of an arc second, or maybe even millionths of an arc second, but beyond that we just can't possibly measure it because it's not possible to see it from Earth. So we can make some quite sophisticated measurements, and we can, using parallax, work out that stars are thousands of parsecs away, or maybe even more, tens or hundreds of thousands of parsecs away. We can do that, but then we reach a limit, and believe it or not, there are stars that are even further and further away. So we need some other methods to try to work out how far away those stars are. And one idea and one thing that people can do is try to come up with some sort of measure of how far away a star is by looking at its brightness. Now, as this picture here shows, there are a huge variety of stars in the night sky. This section is a section of the sky that's been zoomed in on. All of these stars are approximately 8,000 parsecs away, or about 8,000 light years away from Earth, and they're all different from each other. Different sizes, they're different shapes, they've got different amounts of reactions going on inside them, they're giving out different amounts of light, and they've got different amounts of brightness. So it's a complicated universe. But what we can do is, if we are going to make a big assumption, if we assume that all the stars are the same. Now we know they're not, but go with me here, guys. Assume that all stars are the same. So then that way we're assuming they're the same size, they're the same shape, and they give out the same amount of light per second. Or, here's the fancy word for that, luminosity. They have the same luminosity. So if we're going to assume, I'll put a note here for you. So luminosity, that is it's actually like the power rating. The power is the amount of light given out per second, so the energy released per second. And this is a method that was developed a long time ago. I'm going to talk about a scientist called Huygens, and I'm going to use a little example here to show what Huygens did. So what Huygens did, this was in the late 1600s, was he looked up at the sun. And so for the purposes of this exercise, this candle here is the sun. And he looked at how much light was being given out by the sun, and he thought to himself, well, the sun's obviously really close to us, but those distant stars, those other stars I see in the night sky, they might be exactly the same as the sun, but they're just very much further away. So what if I wait till night time and I look at a star? And I see and I measure how much light is being given out by this star, and I'm going to compare the brightness of this star to the brightness of this star. And I'm going to try to calculate how much closer must this star be to us than this one for them to give out the same amount of energy. And the way that he did that was he looked at this star here, and he actually got some slits of card and made discs and covered up the sun until the amount of light from the sun that he could see, the amount of light that was actually coming through from the sun here, was the same as the total amount of light coming through from this star. And so he could do a like-for-like comparison, seeing how bright this star was and how bright this star was. And that he was then able to put some numbers in and try to come up with a calculation. And he came up with a calculation that this star that he was looking at, and at the time the star he was looking at was one called Sirius. Oh, actually, I'll take that back. It was called Cirrus. He came up with a calculation that this star Sirius was something like 30,000 times further away from Earth. Now, he wasn't correct. He wasn't exactly correct, because he based it on a huge assumption. He'd assumed that it was exactly the same as the Sun. It was exactly the same sort of star, and it wasn't. So that was false. But it was a real breakthrough idea, because he was the first person at the time to come up with a calculation that said, look, it's this far away. It's not just a little bit further away. It's thousands of times further away than our star is. And it sort of started people on this route of thinking, well, actually, hang on a minute, this universe could be pretty big out there. Now, how was he able to do this calculation? How was he able to do a calculation? Well, this was the sort of idea that he was working on. It's the idea that as light comes from a source, it spreads out over an area. So if you're a distance r away, it takes up a certain amount of area. But if you double that distance, you end up squaring the area. And if you triple the distance, you square that. So it's actually got this squared effect, where when you go out further away from a star, that star spreads out in all directions, covering space. It's sort of like, you can imagine there being a big, it was a little bit like the celestial sphere that we saw way back in the first part of the module, there being a huge big sphere that the Sun covers, or a huge big sphere, or an even bigger sphere as we go out like this. So as it spreads out, it goes out in all directions. So it was able to sort of look at the compared brightness and come up with a theory. So if you're really close, it's very intensely bright. If you're very far away, all that energy is being shared out over a much larger area. So of course, it doesn't appear anywhere near as bright. But we know this is problematic, because luminosity is not constant. Luminosity is not the same for all stars. So this is a problem. But if you do find two stars that you know have the same luminosity, then it can be used. So two stars with equal luminosity, this is a good method. And it has been used to good effect, because there are certain stars where you can tell absolutely what their luminosity is, and then you can employ this method of brightness. Now, just a note on luminosity. What does luminosity depend on? Luminosity depends on what the temperature of the star is. Temperature of the star. And it also depends on the size of the star. So the luminosity can change according to the temperature and size. But if we know we've got two stars at the same temperature and the same size as each other, then they're the same luminosity, and we can use this method to study them like this.
Now it's time for our wrap-up. Let's give it everything we've got. Ready? Begin.
Okay, so I'm going to wrap it up, and it shouldn't take me long. We can observe the brightness of stars, observed brightness of stars. And I've put in this word observed. I didn't mention this during the video itself, but it's fairly important. The observed brightness of stars can be used to help estimate how far stars are, or the distance to stars. when parallax isn't working, we need a new idea. If they're too far for parallax to work, we need something else. If we've got two stars with the same luminosity, then this does work. And what is luminosity? Luminosity is the amount of energy released by the star per second, or it's the power of the star, energy released per second. And what does it depend on? It depends on two things really: the temperature and the size of the star.